Hi, everybody. Welcome back to the series of videos on solute transport in BioRT-HBV. I'm Liz Andrews, and this video, the second in the series, will include information about how you set up solute transport in BioRT-HBV. Let's go through a quick overview again of the model structure. We have a diagram here that shows us the conceptual model on the left, and then how the model works and the output that we get. And so we have our conceptual model on the left with a watershed or hill slope represented with the various processes that we might expect. We have input, and then we have surface runoff, we have infiltration, and we have a shallow soil zone. So we have the infiltration into the shallow soil zone, and then fluid and solutes can leave that shallow zone, or they can also infiltrate further into the deep zone. And that's kind of like deep groundwater. And we can have, again, solutes and fluid leaving that zone. And so the HBV model is a bucket type model that does a water balance that takes into account the precipitation and the evapotranspiration. And precipitation minus evapotranspiration is equal to the discharge that we'd see in a stream. So the way that it's set up, it's 3 buckets. We have precipitation input to the top, evapotranspiration leaves the top of the system, and we have the surface zone where we have a certain chemistry and we can have runoff or discharge associated with the flow through the surface. And we can have infiltration from the surface to the shallow zone. And then we have chemistry and discharge from that shallow zone, either leaving the shallow zone in an outward movement towards the stream, or infiltrating deeper into that deep zone as recharge, where again, we have a discharge and a concentration from that zone. And altogether, we can do a flex weighted average of all of the different amounts of discharge that leave the different zones and their chemistries to determine what the stream chemistry is. And so this is just a brief overview of how BioRT-HBV model is set up. And we are now going to look at how we would set up a solute transport model. And again, solute transport is just non-reactive transport. So here we have some reactions shown in the conceptual model, but this will just be movement of a non-reactive tracer through the system. So let's start with the input files that you'll need. For the HBV light or the hydrology model, you need to provide evaporation. So this would be a potential evapotranspiration for the watershed that you're interested in, and precipitation, temperature, and discharge files in precipitation, temperature, and discharge in one text file. And then the model will create the XML files that you see there. We will be providing all of these for the watershed that we'll be using in these test cases. And so you won't need to create this, but just know that this is something that you need, especially the evap.txt and the ptq.txt to run the HBV light model. On the BioRT side, this is what we'll mostly be focusing on in these videos. You'll need important files that will provide database information, our cdbs.txt, our chem.txt, the cini.txt, which is going to provide initial conditions, precipitation chemistry.txt, which is either going to be a numerical experiment or something that's used for a warm-up period, a soil.txt, and to run BioRT, you will also need to have the results output from the HBV model, and it will need to be in the same folder as all of these other inputs for BioRT, so that it knows what the hydrology is doing and can do the chemistry properly. And we're going to go through each of these a bit more in detail, but let's start with the file structure because this is really important for getting the model to run. So here's just an example from my computer in the place that I have installed BioRT. And so you can see we have the source code, and then we have the made executable. We also have then an input folder and an output folder. And so in the input, Here's just an example. This is the watershed that I'm going to run, Sleeper Chloride Base. And so Sleeper's River is the watershed that I'm running. And I've just titled it so that I know what the simulation is for. And then you can see those input files that I just said we needed are presented here. Okay, now we're going to walk through each file step by step because they are super important for getting this right. And most important for solute transport is the chem.txt file, because this is what we tell the model we want it to do. So line by line, the first line is recycle. So it has a warm-up period where it takes the chemistry and the hydrology and it runs it. And the idea is that you get it to a point where the chemistry or the hydrology are not changing. And then you can say you've reached steady state and then you can start your numerical experiment. So here we've recycled 5 times. We've given the model 1 year of forcing, so it will run it 5 times plus 1 extra time. Then activity, this is for basically whether you have a high ionic strength solution or not. And so if you have a high ionic strength solution, you might need to do an activity correction to relate activity to concentration. Here we've set the value to 0, so there's no correction being done. Transport only, this is important for us in these simulations. We don't want to do any reaction. So when we have the mode set to 1, we have transport only, which is what we're doing here. And this is only suitable for stable tracer transport problems. If you want to do reaction, you'll need to set transport only to 0. Precip chem tells the model whether it should look for a file that would provide daily precipitation chemistry, or if it should just expect a constant precipitation chemistry defined in the CINI.txt. Here we've provided 1, so that's saying that we will provide a precipitation chemistry time series. The next line is numerical experiment, and that just says, do we want to change something in our chemistry file and run it as an experiment? So we've set that to 1 because yes, we would like to test some different things. And then temperature provides just 25 degrees C, and that is what it does all the calculations based at. Then in the chem.txt below that, we have primary species. And so there will be a video that you can go back and look at for describing what primary and secondary species are. But here, just know that we are listing all of our primary species, and you always need to have pH. And here, chloride will be our non-reactive tracer. And so chloride, as our non-reactive tracer, is the solute that we are most interested in tracing through the system. And it's important that when you have these primary species, they exist in your CDBS file. And again, that will be covered in a video that you can go back and look at. We don't have any secondary species here because we are only interested in the chloride. And again, we don't have any mineral kinetics because we don't have any minerals or reactions occurring. The next file is the initial conditions, and this is provided in the CINI.txt file. And so basically we tell what the system should expect. We take those primary species in each of the different zones and give them a concentration. So in the precipitation, the pH is 5.5, and we have 1.7 times 10 to the negative 6 moles per liter of chloride in the rainfall. Then in our upper zone, we have the same pH setting, same in the lower zone, and we have essentially no chloride present in these conditions. And you just can't assign 0 because numerical models don't love having zeros, but you can set the value very small and it essentially replicates a 0. The next file, because we told it we wanted to do precipitation chemistry, we have precip chem.txt, which is going to be used for the warm-up. And then we have the numerical experiment precip chem.txt. In the precip chem.txt, we have a constant pH and chloride provided daily for the entire time series. So this is 1 year, and it will get repeated 6 times. And then our numerical experiment precip chem On day 7, this 2009, January 7th of 2009, we have increased the chloride by 3 orders of magnitude. So that's the experiment that we're running. How long does it take for that to move through the system? Then our soil.txt file provides important context about the subsurface. Here is where you can assign parameters to the soil to represent how much water is present there. So we have values for porosity in the upper zone and lower zone. We have passive water storage in the upper zone and lower zone. And then we have depth in the upper zone and lower zone. And again, these parameters just control how much water is present in each of the different zones. So these are just the background on the input files that you'll need to run the solute transport simulation in BioRT-HBV. The next video will look at actually running this example in the model and then examining the results from that. So thanks for tuning into this video. Be sure to check out video 3, where we'll actually run the model. Thanks.